Pluto was prepared for this from the beginning. It was never part of the solar system's planetary hierarchy. Its orbit intersects with that of other planets, which is unusual for a planet. The mysterious dwarf planet Pluto, located at the edge of our solar system, is causing quite a stir in the astronomy world. Recent reports suggest that it is on the verge of colliding with Neptune, raising concerns among scientists and space enthusiasts alike. Prominent experts, including Neil deGrasse Tyson and Michio Kaku, are warning of the potential consequences of this celestial collision. But how exactly did Pluto collide with its distant neighbor, and what could this cosmic collision mean for Earth? Join us as we learn about the terrifying events unfolding between Pluto and Neptune. Once considered a full-fledged planet, Pluto was later reclassified as a dwarf planet due to its unique orbit. Despite this change, it continues to fascinate and engage the astronomers. Recent predictions by prominent scientists including Neil deGrasse Tyson and Michio Kaku highlight the incredible proximity between Pluto's orbit and that of Neptune. These experts warn that a collision between the two planets could pose a serious threat to Earth. What makes Pluto's journey around the Sun unique is its unprecedented performance in our solar system. Pluto's orbit lasts 248 years, and Pluto has not completed a full orbit since its discovery in 1930. Adding to its curiosity is the fact that its path is highly elliptical, departing from the nearly circular orbits of the major planets. Pluto's orbit is also tilted 17 degrees relative to the ecliptic, making its path appear steeper than that of the other planets. This combination of tilt and elliptical characteristics adds complexity to Pluto's orbital pattern. A notable aspect of Pluto's orbit is its intersection with Neptune. During each orbit, for about 20 years, Pluto moves closer to the Sun than Neptune, defying expectations based on their respective positions in the solar system. This raises the question, why has there been no collision between Pluto and Neptune? The explanation lies in the gravitational influence exerted by the other planet. The study of Pluto's orbit began shortly after its discovery, and it presented astronomers with a mysterious trajectory. Unlike most planets whose orbits are relatively close to the ecliptic, Pluto's unique features are its steep inclination and elliptical shape. The mystery deepened when it was discovered that Pluto's orbit intersects Neptune's orbit. Despite this complexity, the stability of Pluto's orbit serves as evidence of the inherent complexity of cosmic dynamics. The three-body problem in space involves understanding the motion and gravitational interactions between three celestial bodies: Pluto, Neptune, and the Sun. This is like predicting a trajectory based on initial positions and mutual gravitational influences. In the case of Pluto, this problem reveals the complex interactions between Pluto's path, Neptune's path, and the Sun's gravity. Terms like azimuth oscillation, latitudinal oscillation, and VZK oscillation help solve this astronomical puzzle. Astrophysicists argue that azimuth oscillation, which serves to keep planets in orbit, plays a significant role in the context of Pluto and Neptune. This term refers to the fact that when Pluto passes through Neptune's orbit, it is at least 90 degrees from Neptune, essentially preventing a potential collision. The latitudinal oscillation, which describes the vertical motion of a celestial body in its orbit, ensures that Pluto is well above its orbital plane when it approaches Neptune or another giant planet, providing an extra layer of protection from collision. A key element in understanding celestial motion is the VZK oscillation, named after three scientists, von Zeipel, Littow, and Kozai, who studied the gravitational interaction between three cosmic bodies, Pluto, Neptune, and the Sun. The VZK wobble explains why Pluto's orbit around the Sun seems odd, but remains smooth over time. Despite the apparent chaos of the universe, underlying patterns and rules maintain order. These factors combine to stabilize Pluto's orbit, preventing it from colliding with Neptune or veering off course. Numerical simulations from the late 1980s showed that despite its stable nature, Pluto's orbit is technically chaotic, with small initial perturbations causing large differences over millions of years. However, Pluto's unique orbit maintains stability over incredibly long periods of time, controlling the chaos. Recent computer tests have improved our understanding of how the major planets Neptune, Jupiter, and Saturn affect Pluto's path around the Sun-Neptune special conjunction, which completes 3 orbits for every 2 orbits of Pluto, promotes stability. Jupiter's gravity also plays a role, while Saturn has a lesser influence. Overall, these tests show that the combined influence of Neptune, Jupiter, and Saturn ensures Pluto's safe and stable motion through space for billions of years. These phenomena are important for maintaining order and predictability in the motion of celestial bodies in the universe. Without these mechanisms, the solar system would be a place of greater chaos and unpredictability, potentially causing collisions or ejections from stable orbits and having ripple effects on other celestial bodies. Understanding Pluto's orbit is especially important as discussions of a possible future collision with Neptune continue. This knowledge provides a clearer understanding of the dynamic nature of the solar system. The case of Pluto highlights how seemingly unstable orbits can be balanced by the complex interplay of gravity and orbital dynamics. Ongoing observation and study of these phenomena is essential to better understanding our place in the universe. Exploring the depths of space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which shows the sensitive dependence of a celestial body's path on its initial conditions, is clearly demonstrated in the case of Pluto. Even small changes in the dwarf planet's position or velocity can significantly alter its long-term orbit. Computer modeling has played a key role in helping scientists understand how Pluto moves through space. These simulations use complex mathematical models to simulate the gravitational interactions between Pluto and other celestial bodies, such as Neptune. By making small changes to the simulations, astronomers can observe how small changes can greatly affect Pluto's orbit. In the late 1980s, these simulations revealed an interesting aspect of Pluto's path. Despite features such as azimuth and latitudinal oscillations that contribute to its stability, Pluto's orbit can still exhibit unpredictability. Small initial differences in Pluto's position or velocity can lead to large changes in its path over several years. Despite this inherent chaos, Pluto's orbit remains exceptionally stable for billions of years. This suggests that Pluto's seemingly irregular journey around the Sun follows a structured order. Predicting cosmic events is particularly difficult for planets like Pluto, which have unpredictable orbits. The inherent unpredictability of these systems makes long-term predictions uncertain. Numerical modeling can help us understand and predict the future paths of celestial bodies, but it also exposes the limits of our predictive power. These models rely heavily on precise initial conditions and complex interactions in the model. Even small errors can lead to large variations in the results, making accurate predictions difficult. The chaotic nature of the orbits of objects like Pluto reminds us of a universe that is constantly changing. While we have made progress in understanding the universe, the case of Pluto highlights the limitations of our current knowledge. Understanding the gravitational influence of the giant planets in Pluto's orbit provides valuable information about the broader dynamics of the solar system. It shows how the presence and position of each planet can affect the stability and trajectories of other objects in the system. Despite these complex forces, leading astrophysicists are now expressing concern about the possibility of a collision between Pluto and Neptune. This raises the question of why a collision that seems unlikely given these complex dynamics has now become a problem. Neil deGrasse Tyson, a renowned astrophysicist who has played a key role in popularizing astronomy, offers a unique perspective on the mysteries of the solar system, particularly those related to Pluto. Tyson, who famously reclassified Pluto as a dwarf planet rather than a full planet, shares insightful thoughts on how our understanding of celestial dynamics is constantly evolving. Tyson sees Pluto's reclassification not as a downgrade, but as a necessary adjustment to our growing knowledge of the various objects orbiting the Sun. His approach to celestial dynamics involves continuous learning and adaptation. He sees the complexity of orbits like Pluto as a reminder of how much there is yet to be discovered in the universe. Tyson believes that it is this unexplored fascination that makes astronomy so fascinating. Tyson also knows how space-related events and discoveries shape the public's interest in astronomy. He believes events like Pluto's reclassification and its unusual orbit are opportunities to capture the public's imagination and curiosity about the universe. By discussing the dynamic and sometimes counterintuitive aspects of cosmology, he opens a window for the general public to marvel at the wonders and mysteries of the universe. Collaborating with other scientists, Tyson actively warns the public about the potential dangers of Pluto's unpredictable path. After studying Pluto carefully, he expressed fears that the three-body problem could be a real threat, suggesting that a collision with Neptune was long overdue. Furthermore, he emphasizes how such a collision could upset the balance of the universe and have catastrophic consequences for Earth. A collision between Pluto and Neptune would be an unusual and catastrophic event in our solar system. This collision would release a tremendous amount of energy and would likely destroy Pluto due to its smaller size and icy composition. Debris from the collision could be scattered throughout the solar system, posing a potential hazard to other planets and moons. In the case of Neptune, such a collision could potentially alter its atmosphere and orbit, depending on the specific details of the impact. Michio Kaku, a theoretical physicist known for his work in string theory and popularizing science, offers a unique perspective on this scenario. His views on the future of space exploration and the connection between celestial dynamics and theoretical physics provide deep insight into phenomena such as Pluto's orbit.